Okay. So, last lecture I had mentioned the J function, and but I did not remember the exact coefficient. So, just for completeness, I mean you are not expected to memorize these numbers or anything. Let us look at the coefficient of Q, which is 196,884, and it can be written as this, and what this implies is that this particular number is special to the monster group. If you try to find a matrix, which non-trivial matrix representation of the group, the smallest one you could find, which is irreducible, is of this dimension. So, it is very difficult to cook up. I mean this number is not just cooked up, and 1 means singlet, it means it is trivial. So, you just take a 1 by 1 matrix where every element gets mapped to 1, okay, and then so that is a trivial representation. So, this is also the next representation, bigger representation. So, it is sort of mysterious why these numbers come, and this story, it's sort of, this is a story, it is a popular book with not too much mathematics by Mark Ronan. It is Symmetry and the Monster. It is a fun read and I recommend it, and let me give some references for group theory. The first one is Michael Arthan's book on algebra. It is actually an undergraduate linear algebra book. It has some stuff on group theory. It also has lots of things on linear algebra. I would recommend, if you do not know many of the things, to work through it. Okay, this, and J.S. Milne has actually a lot of stuff on his website, which I have given the link out here, and for group theory he has a nice sort of 150 pages of notes which you can read through, and he has some exercises, and I would recommend sort of working through some exercises so that you understand the ideas which go. There is no shortcut to that. I mean if you just keep there are so many books on group theory you can keep, the list can keep going on and on, but what I recommend is that actually playing around with things. I will also probably give you an assignment on finite groups, so that you can play with some specific examples that I see fit. Okay, so this is all I have to say about group theory, but outside of class somebody asked me this interesting question: do we really need so much abstraction? The short answer is yes. The longer answer is that if you there is no getting around the fact that symmetry in nature is captured by this wonderful idea called group theory, and the first sort of important use of it was made by Wigner in physics, and since we will be looking at relativistic field theories, which is usually used in the context of high energy physics, there again the whole development of the field actually made use of group theory. One important instance is called the eightfold way. So, people were looking at nuclear resonances, and there were plenty, I mean every day they were finding one, and the question was, is this a new particle, is it some, maybe I can name it after my wife or whatever, things like that did happen. And so, but there was Gell-Mann, and at some point realized that there was some group theoretic structure, and the group which actually sort of made him organize things was what is called SU3, and the eightfold way refers to the fact that SU3 has an 8-dimensional representation, and certain set of objects could be organized in a multiplet of size 8. Okay. Another place where you would see, you might have already seen, is if you have done quantum mechanics, you have the angular momentum algebra, which you would have seen. Again that is a very important use of the group, rotation group in quantum mechanics. So, there is no getting around the fact that group theory is something which is very important, and the idea here is to do things in abstraction, because in some way that is the easiest. The thing is, if you are able to digest the fact that there is a representation of a group and it has certain dimension, the minute I say something like the 8-dimensional representation of SU3, I mean that is actually a very well defined statement, and as this course goes along you will also learn more about these things, and you will become more comfortable with it, and you will realize, yes, this is the only way I could say it. Why should I spend 25 minutes trying to explain what this 8-dimensional representation is, when it can be said in one line, and it is very precise, and this is the kind of precision we will need and we will use. Okay. So, the sojourn into finite groups was to give you exercises which you could play with and do some things more quite explicitly. Okay. There is not much you can do explicitly in general, because you need a little bit more of theory to see the structures, which we will see as much as we need. And another point for doing the math in this course is because we would like to I mean if you take group theory, it is a full course in a maths department, but look, we want to just learn enough group theory to get by. Okay. And depending on your personal interest, you can read up things, though nobody is stopping you from that, but what the goal of my lectures here is to fill in the math background, because most of you have a mixed background, and so you know some things, you do not know some things, but at the end of the day I cannot assume that everybody knows everything. So that is one more reason to actually spend some time on the math that is required. Okay. So actually today we are kind of ready to actually start working towards descriptions of continuum field theories. Okay. So classical field theory, as we saw in the very first lecture, was the classical mechanics of fields. By the way, there is a wonderful book titled Statistical Mechanics of Fields by Kardar. I recommend reading chapter 2. Okay. It is not classical, the title of the book is Statistical Mechanics of Fields, but we will be doing classical mechanics of fields. Okay. So this is recommended reading, it is a wonderful book. So the basic object is going to be a field. So I am just using a symbol phi of x, and of course it could be t. For simplicity, for a few minutes I will assume that we have only one dimension, because I can draw, I can use the board efficiently then. Okay. So in other words, x takes values in some real line, and at every point, so let us say this is a scalar, so at every point there is a scalar degree of freedom. So clearly there is an infinite degree of freedom, and so how do we go ahead and handle it? One trick is to actually discretize space and then take the limit where the spacing goes to 0, and that is what we will do. So we will replace, so this is R, I will replace this by a discrete set of points. So it is an integer worth of points, and let us say they are equally spaced with some spacing a. Okay. So we start, so this is something which has coordinate x, but this would be some typical point would be x equal to some where n belongs to integers. Okay. And important things like, if you believe that there is translation in the x direction, clearly it is broken out here, it is broken down to the discrete set of translations in this one dimensional lattice, okay, by units of a. But what we have in mind is that what we will do later is to take a to 0, so that the spacing goes away, and hopefully we will require this sort of a symmetry. Okay. So first step is to ask what happens to phi of x. Okay. So we have done some thinning, so what we are going to do is we will only know the values of phi at these points. So let us write out something like this. We replace phi of x with, in the discretization process, by q of n, which should be, morally speaking, I am not using the equal to sign, you will see why, we will put the equal to sign later. This is has the same as the degrees of freedom n of a. Okay. So what I have done in this process is to convert the degrees of freedom to make it look like a system which has infinite a normal classical mechanical system which has infinite degrees of freedom. Okay. So the question is, what do we do with the, so let us recall the Lagrangian. Actually, even before I do that, let us take a slightly let us take a toy model of the kind you would see in Kardar's books, for instance. So just take bunch of degrees of freedom which lie out here and think of them. So these are like masses connected to by some springs, that means their interaction is harmonic. So what I have in mind is, so you have some, so the Lagrangian for such a system would be so this would be the kinetic energy part. Okay. You could have a constant here, but let us say I normalize things such that this constant becomes 1 minus the potential energy which would come from the spring, which would look like summation over I half. Okay. So let us say k, let us use a small k by 2 okay. So this is a so I am just saying that this is some harmonic spring with spring constant k. Okay. But if you think of this as some ion in some lattice, there will be some local potential which will keep it out there. So I could write something else which would also okay. So let us look at each of these terms again. First point to realize is that each of these terms is a translation invariance. So we are assuming this an infinite chain for practical purposes. So you can see that when the discrete symmetry is just I goes to I plus 1. So I have so it is not like I have different constants for each of these things. So this coefficient is uniformly 1. Similarly out here all the springs are identical. Okay. And this potential at everything again side should be identical. So let us look at these two so this is the normal kinetic energy term. If I had put an m out here, then you would be happy, but let us say I put m equal to 1. So so let us look at this particular term. This term involves two sides, okay, but this involves only one side. So now you can see that, but these are all local interactions. There is nothing which says that something here and something which is like million lattice points away, there is no interaction between them. This is kind of intuitively what we would write. We could have, I mean, without losing sleep we could have made this as I plus 2, but okay, I mean, but this is more natural to this kind of problem. So we will distinguish, but there is a difference between these two kind of terms. This term is local, this is also local, but this we will call ultra local because it is determined by the degrees of freedom at a particular site. So we will call this term ultra local. All this is in space, all these statements, while a term like this we will call local. Okay. So now comes the question, how would you go about taking the continuum limit of something like this for starters. Okay. So of course the easy answer is say take a to 0, okay, but now comes the issue, how do we take a to 0, okay. So first thing is to realize, so yeah, it is not enough to take a to 0, we need to know what is it we have to do to this summation over I. Does anybody have any idea what I should do to that? You replace it by an integral, okay. So, but this has dimensions of length and this is dimensionless. How do I fix it? Okay, you go back to the old definition of things. So, you put a 1 by a out here. Okay. So, now let us go back and first pick up the kinetic energy term. Okay. So, let us look at the Ke term. Okay. So, okay. So, this says that I should go ahead and replace summation by 1 over. So, this just becomes 1 over 2 a integral over x we are not done yet. We need to take the continuum limit, but you can see that if I take a to 0 just naively, what do I get? I find that it blows up. Okay. But we can take care of that by realizing taking advantage of this particular thing. I said q need not be exactly equal to this. Okay. So, we just go ahead and define. So, we say that let phi of x be defined to be so you can see that what I have to do is you have to take a limiting process or whatever, but if I define it this way, okay, I get so x equal to yeah, thank you. I just need to put a square root, right, because there is a square out here. Okay. So, it is important to note that this is your continuum field and this is the discrete field. So, there is always some power of A which goes with the field, and in fact suppose we had instead of one dimension, suppose we had d dimensional space time, then let me use a different color and write that. So, for d dimensional space time, you would not sum over just I, you would sum over the d dimensional lattice. For simplicity, let us assume it is a cubic lattice of size A. Okay. Then sum over the lattice. So, d dimensional cubic lattice, I will not write cubic, should go to 1 over a power d okay. So, this is what you get for in the summation. Now, you can see that the analogous statement which I will again write now, that would be that phi of, now I will just use x because I would require many indices n1, n2, n3 etc. So, okay, let us do that. Okay. So, let us say that it is n1, n2, nd. So, what I have in mind is I do not want to write out. So, I will just in this notation this would be just n1 would be just there will be only one n. So, there will be many of these guys out here. This should be equal to 1 by a power d by 2 q of that vector n. Okay. So, you can see that the dimensionality of your space is actually buried into this. Okay. So, let us get back to the rest of the terms and we will again work, let us see what we have to do to take the continuum limit of these terms. So, the next term would be the local term, So, now again we can see several things. First thing is we know that the summation has to be replaced by the integral, but now we also have to take into account what happens to this difference. Okay. So, let us first work out what the difference looks like. Again I will do it for just one spatial dimension, and I think it is a simple exercise for you to work it out for the other dimensions. Okay. So, so let us look at what happens to a term like this. Okay. If I divide this by a and multiply it by a in the continuum, okay, what will happen? You can see here is that we are seeing the appearance of the discrete derivative. So, in the limit that q goes I mean a goes to 0, this becomes the derivative. Okay. And putting in that other factor that we have out here, that is square. So, and q is equal to square root of a times phi. So, this should become this, there is one a coming from here, and there is also a square root of a coming from the scaling which you need to go from q to phi, and this and the way I have written it, it is q I minus q I plus 1. So, that will be minus of the derivative. Okay. So, let us just now we can put we can combine, we also will get some more powers coming from this thing. So, this term now, so you get, since there is the square of this, you get this is what, a power 3 by 2. So, you get a cubed coming from this part, and the summation will give you a 1 over a. Okay. So, now we can see that so again taking a equal to 0, you can see that this term is now going to 0, but now you could say fine, that means such terms are irrelevant, but that is not quite true. You do not want to lose your local interactions. So, again you scale things, in other words take k to 0, k to infinity, such that a becomes a goes to 0, such that this combination whatever k a square is some constant. Okay. So, the limit is, let k is defined to be limit a tending to 0, okay, k tending to little k tending to infinity, such that this combination which is k, this should have a finite limit of course by definition. But you also know that springs become stiffer as you make them smaller. So, this is not it is not counterintuitive. Okay. So, this tells you that this, okay, so this is another thing. So, now we can see that the local term becomes, the local term is now nice, it is half k, okay, there is a minus sign in the way it appears there, okay, but I am just looking at this term is now half k integral okay. We still need to handle the ultra local term. So, what I will assume is that the ultra local term has some power law. Okay. So, let us say let v of q be some let me use some lower case, not I, okay. Okay, it is some power m. If you want several of them, you can sum over them, but I am just choosing for simplicity just one term. Okay, I call this coefficient B m. So now, so that the ultra local term now has the following part, which is half, no half out there. So, it is just summation over I V of q I, this is equal to okay. So, now we can quickly do things. We know summation will give 1 by a, and q, each power of q will give you a square root of a on top. So, this will just tell you that this is equal to or goes to B m, this gives you a power m by 2 divided by a. Okay. Again, it is obvious how to take the limit. The limit is to just take the limit such that so you take now b goes to so you basically take the choose the limit of b such that this thing becomes a constant. So, just define. So, I will not worry about how the limit process goes, we just define B m to be okay. So, now we are ready to write out the Lagrangian. What I will do now is to write the action first instead of the Lagrangian. Oh, let us write the Lagrangian, it is okay, let us write the Lagrangian. So, the Lagrangian in the continuum limit is the sum of 3 terms. The first one is this, so it is just half. Okay. And the important point here is that so it is very clear how to do this for an arbitrary function. You can scale things properly and get everything to work out, okay, if you have some polynomial kind of thing. Okay. So, this is what you get, and we have already put in locality in space. How have we done it? We have seen that we have only taken nearest neighbor interactions, and we have got an integral over only dx. An example of a non-local term would be something. So, it is useful to see how a non-local term looks like. I am not saying this is the only non-local term, I am giving you an example of a non-local in space, that is if I have something like this times some function of x and y. So, it depends on 2 points. You can make things even worse, you can make it depend on n points, okay, but this depends only on 1 point. So, we have already put in locality, and it shows you that locality in space implies that there will be only 2 kinds of terms that you could add. One is a local term that can be expressed in terms of derivatives of x, I mean phi and its derivative, I mean derivatives of phi, and the local pieces are the derivatives of are no derivatives, but just ultra local terms which are functions of phi. Okay. So, this sort of gives you the idea as what kind of Lagrangians you have. Okay. So, obviously since what you have inside the braces, it is natural to call this object a Lagrangian density, because dimensionally it is really per spatial thing, right. So, one writes this thing as integral dx, okay, we use a script L. Okay. In fact, there are more general local terms that you could write. I could write higher powers of phi, and there are models where people do look at such terms. So, I am just I will write a something like that, let us just call it k prime over 2 over some power, let us call it z, okay, where z is some, when z is equal to 2 it is this, but z can be greater than 2, anything higher powers. Okay. So, now we can ask this we did only for one dimension. The generalization to d dimensions is quite easy, but once you go to more than one dimensions, even if you are in 2 dimensions, you have additional symmetries to think about, which is rotation. You would like to think things to be isotropic in space. So, things have to be rotationally invariant, and you may wonder how do I implement that. We can implement it just like we did by implementing translational invariance. We required things to be invariant under translations, the action to be invariant under translations. So, a term like this you would just replace it by the scalar product. Okay. So, for instance, in higher dimensions, higher spatial, dimensions, dx of phi. So, for instance, we could have taken in one dimension dx phi whole cubed, there is no issue, or so it seems. You can take an odd power, but if you go to higher dimensions you will have to take square roots to do that. So, dx square would go to some kind of gradient, let me write it as a dot product. Okay. And you can see that no particular direction is special in such a term, isotropy is taken care of. Okay. So, if you want to put higher powers you can, but it has to be some power of these sort of guys. Okay. And needless to say, L will become okay. So, the continuum limit of that simple model of springs tied together would be some would be a string with some tension, right. And so, in such cases this k, what would k be in such in that example? What would k be in that example? K would be the tension. Okay, yeah, it related to the tension, but also related to the speed of sound on the thing. Okay, so k is some kind of, even by simple dimensional analysis you can see that k should be the square of k would be the square of some velocity or speed, to be more precise. Okay. So, that is just dimensionality. Now we can come back, I mean there were all these, I erased one of these things. The question is, can we figure out is there some way of making sense of these numbers, these powers of A. So, let us write out what are the powers which we got. We got 2 from here, we got m by 2 minus 1 from here, and the last bit was with phi had a square root, right. So, this is roughly the, so this has a okay. So, now question is, can we come back look at this Lagrangian and derive the same thing, and I will show you how to do this. And the way to understand that is, at the lattice level I could have done the following thing. I can take A to lambda A, I scale it, okay, and so we can do the same thing in the continuum by just realizing that I just go ahead and scale x. Okay, so I scale, so I replace this by x goes to lambda x, and you want to associate demand that every term is scale invariant in some sense. So we start from this guy and let us look at this. So x, so this implies that dx also scales like lambda dx. So you look at this part, t does not scale, so only phi has to scale. So it implies that phi should scale, to cancel that phi should scale with okay. Now that this term has fixed the scaling, we will call this thing, we will call this half or minus half actually to be precise, is a scaling dimension of the field phi. What about here? So now you can see, so there is an d by dx here, so this will go like 1 by lambda out here. So there are two of them, that will give you a 1 by lambda square, and a phi gives a square root. So you get a 1 by lambda, so you phi goes as, thank you. Okay, so then k, yeah, so k, so now you can see that k is, so dx of phi whole square will go like this, will give you a lambda power minus 2, and phi will give you a lambda power phi, this will give lambda. So the only way things can be invariant is if k scales like, so this implies that k scales like, it has to cancel this k lambda cubed. There is a lambda from the dx which will reduce this number to 2. Okay, thank you. And k, so let us forget this. So we have to look at Bm. So Bm will have to go like phi m is like so it goes like lambda power minus m by 2, and but it has to also, I have to flip sign I think. Okay, okay. So you can see that it is not as if these things we scaled away. So let us see what we get out here. Is this, I can't see that, so okay. So you can see that you get the same scaling dimensions which you have, which you had out here. Okay, so it is not like by going to the continuum we forgot, we got all the memory of those limits, we can actually recover these things. Okay, and these are called the naive scaling dimensions. Okay, they are called naive because quantum mechanically these dimensions can change. Okay, this is not something which we will do in this course, but okay. So there is some memory even after you take the continuum limit in this Lagrangian. Okay, is this clear? So now, but we are interested in constructing Lagrangians for relativistic theories which have relativistic symmetries, that is a Lorentz group. So we have already inputted spatial rotations, we have taken care of. Even if you look at the Poincare group, we have even got taken care of translations. In fact, translations in space and time are taken care of. Okay, if you go look at the level of action, so action you can see is an integral over these things. So now the question is, how are we going to, so we need to ask what is the value of k such that k or all these constants such that we end up with things which are Lorentz invariant. Okay, so we need to only ask how they transform under Lorentz Boost. Okay, so first thing is let us start, what I will do now is to start from the easy part. Let us start from the ultra local term and ask the following question. So let us take the ultra local term. Okay, and what I will do more generally is that you can replace this by a function which we will call it u of phi. Okay. I call it u because u is stands for ultra local, to remind you, not v but u. Okay. So, the ultra local term is u of phi, okay. And we have said phi is a scalar field. By that we mean it is a scalar, since it is a scalar under Lorentz rotations, transformations. Any arbitrary function of it is also a Lorentz scalar. Now, you may think that I can consider the local term, I can just write out a local term, which I look at only the local term and try to make things work, but we know that under Lorentz boost space and time mix. So, clearly there is I mean terms like this can become terms like this. So, we can ask how things change. Okay. So, let us go back and look at how. So, we have, let us say that x prime is equal to okay. So, this is Lorentz boost. So, the question is what happens to d by dx prime. Now, we can use the chain rule and maybe I will go the other way, go from d by dx okay. So, we can just look at these. So, dx prime by dx is just cos hyperbolic. Plus this should give you some sine hyperbolic with some factor of c, dt prime by this is 1 by c. Let me shift the c to this side. Oh yeah, yeah, thank you. Yes. Let us put psi. Thank you. Okay. So, d by dx is x prime and t prime, okay. And it is not hard to work out what d by d prime is. Okay. So, now comes the nice stuff. So, this we can see. So, the question is, so we have to ask how this transforms. So, by acting on this thing you can see that I can put the phi inside this. okay, and not hard to show that the Lagrangian density involving derivatives, the part of the is invariant under the Lorentz boost if so that is the case. So, basically what you will see that the cross terms vanish and the nice identity cos hyperbolic square plus sin minus sin hyperbolic square equal to 1, and the nice thing is that there is this minus sign. This minus sign is very important. The reason is that from our, if you go back to our discrete system, this was part of the potential. Okay. You also learn one more thing, if you put a term where like this where z is not equal to 2, it is not invariant. You cannot choose some random thing which you could have if there was nothing which mixed space and time. So, theories like this would usually happen in non-relativistic settings. These are Lifshitz, these are called as Lifshitz models, and there is no space and time do not have to mix in this fashion. Okay. So, you can see that arbitrary terms like that are completely ruled out. Okay. So, now we are sort of ready to write out the most general relativistic okay. So, L okay. And so I have just read it, I have just solved for everything. So, this is what you need to do. The only change we did, we threw away that kind of piece and we have got this, and now you can we can also see the generalization to arbitrary d dimensions is to just write this and replace this with gradient. Okay. But this term actually can be written in a very nice manner by recall that I can pull out a c square fully. So, this will become d by dx0, recall x0 is defined to be Ct. Okay. And this has a nice way of, you can rewrite this as C. Okay. So, in relativistic field theories you can see that since these two terms mix and they can be written as this. So, this you can see is explicitly there is contractions, this is by manifestly a Lorentz scalar. Do not worry about this factor of c, you can, if you wish, you can rescale, you can absorb one c into the dt definition and the other c can be absorbed into the taken in with the phi, so that the c goes away. It will and you can absorb all the other constants. So, that is not so important. What is important is that this is manifestly a Lorentz scalar. So, in this course for the rest of this thing, I will, when we mean what I mean by kinetic energy, we will refer it to this term itself as the kinetic energy. So, it is a loose imprecise thing because really this is what you would have thought was the kinetic energy part, and it contains the local part as well. Okay. So, we will call this kinetic energy, this is standard convention, and the ultra local piece we will call that potential energy. Okay. So, this is how you would write things. And one more thing you can see is that if you even though the Lagrangian, this measure d dx is clearly not invariant under just Lorentz transformations, the full action is, because the action becomes, so I can write, so S is integral, so I am including time and this thing times some Lagrangian density which depends on phi and d mu of phi, and so this, of course, this measure is also trivial nicely Lorentz invariant measure, and this term by term we saw was a Lorentz scalar. So, what we have accomplished today is to write out what would be a local Lagrangian which describe for a scalar field. Okay. So, you can ask what about vector field, and the answer is yes, we could write these things, but what you can see is that this kind of thing will still go through, that you would write your action as some integral over both space and time, and it will be in terms of some Lagrangian which would be in terms of the field and its derivative. This structure will still hold. Okay. Yes.
For a Lorentz invariant scalar field, will this be the only possible structure, kinetic and potential term?
Yes. You could get higher powers.
Yeah, in the potential term, but anything else?
Not just in the potential, you can write the whole thing power, higher power you could write, but this combination you cannot separate. There is
so
nothing.
be some function of the kinetic energy and some function of the field, or potential energy.
Yes. Absolutely. And just as, I mean, if you, one more thing I want to remind you is that in quantum mechanics, why did you restrict yourself to 2 derivatives? You could have had 3 derivatives, etc. Suppose you had q double dot square in your thing. What you usually do there is to introduce a new extra degree of freedom, whose equation of motion is just saying, so if there is q triple dot, you introduce some other, let us say q prime, which is equal to q dot, and then you rewrite stuff, and then you will get something. So, you add you sort of increase the degrees of freedom to handle lower derivative pieces, higher derivative pieces, and write it again as a normal Lagrange. So, these kind of tricks can be done, and so, but actually the hardest part in any system is not writing the Lagrangian density, it is the first step itself. What are the correct degrees of freedom for to describe your system, and that is the hard part actually. And once you have the correct degrees of freedom, then anything of, I mean, so you could, the same system may have at different energy scales different Lagrangian descriptions. And classic example is QCD. At higher energies, its best its theory of quarks and gluons, but low energies is actually it's more like a theory of mesons and baryons. So, you could write some other theory. So, the fields which you would describe low energy stuff would, you can write effective Lagrangians which actually do these things, and there is a lot of interesting work which works that way. So, you can see that the same what you thought was the same system at different energy scales behaves like the degrees of freedom, natural degrees of freedom are different. Another example is the superconductor. I mean, in its normal state it is a system which contains only electrons, but in the superconducting state there are other degrees of freedom which carry the thing, and that is what leads to superconductivity, the Cooper pair. Okay. You think of that as a different degree of freedom, and it is funny that the Cooper pair is a bosonic degree of freedom, even though the individual parts are fermions. Okay. So, you would describe that by a scalar field theory, even though, I mean, you might say, oh yes, all the conductivity is due to electrons moving, but it is like 2 electrons moving in synchronization, and it does not make sense to think of it as a system of electrons, but rather the scalar field which describes this thing, okay, the singlet part in some sense to be precise. Okay. That could be the triplet which could give half, that is also a scalar. Okay. So, that is actually the hardest part in real systems. Okay. I am done.